Welcome to Big Idea 3. We're going to be talking about reactions. And it's going to start off back in chapter 3 in our book when we get stoichiometry. You need to know how to balance equations. Oop. And then we need to know how to do stoichiometry, and if we just cover limiting reactions, that will kind of cover everything else. So if we had a balanced equation, let's do nitrogen plus hydrogen makes NH3. Let's make this a little bigger here. We need to handle some numerical calculations with this. So if we had, it's really common to have things in grams. If we had 7 grams of nitrogen and 3 grams of hydrogen, we want to know how much ammonia we can make, how many grams of ammonia. There's lots of ways to do this. You can do it with dimensional analysis and convert grams to grams of each one separately to see how much they can make. But then the questions always come up, how much of the excess reactant is left over. So we had other ways to do this by doing mole charts. If you keep track of all the moles of everything, you can kind of do it all at the same time. When you convert that nitrogen to moles, you have 0.25 moles of nitrogen, and the hydrogen is 1.5 moles. And we don't have any ammonia to begin with. That's at the very beginning, the B. The change for those, their coefficients are going to be, it's a 1 to 3 to 2 ratio. So we need to consider that when we do our math, and this makes a little bit more sense now that we've done equilibrium. Nitrogen is going to go down by X. Oh. Let's change that. The hydrogen is going to change by 3x, and the ammonia is going to go up by 2x. One of these is going to go to 0. Either the nitrogen is going to go to 0, or the hydrogen is going to go to 0. You're not allowed to have negative numbers because you can't have negative matter. So your job is to kind of figure out what these x values could be, either by nitrogen or hydrogen, and then kind of carry it forward. So if we have 0.25 moles, x in this scenario would be 0.25. So if we took it over to the hydrogen, minus 3 times 0.25, 0.75, it looks like that gives me a leftover hydrogen. So nitrogen is going to be my limiting reactant in this case. And then I would make 2x, so 2 times 0.25. I'll make 0.5 moles of ammonia, and then we could convert that back to grams. So really simple limiting reactant calculations we're going to need to be expected to do. But when we have those moles, when we're doing stoichiometry and conversions, we can really convert those moles to anything. So we just saw we can convert to grams if we had a molar mass on the periodic table. Grams to moles, very, very common. If we had coefficients like we were just doing in that other equation, we can convert to moles of another substance using a balanced equation. Some other ones that we're going to do are we can do Avogadro's number. So that would be atoms, molecules. We just generically say particles. How many individual things are there? And that is our definition of a mole. 6.02 times 10 to the 23rd power is 1 mole. So we can convert to individual atoms or particles. We can convert to volumes of aqueous solutions if we had a molarity. We can convert to volumes of a gas through the ideal gas law, PV equals nRT. Or, and this only works at STP, 22.4 liters per mole. That's only at STP that we can do that conversion. And then the last one we can do is we can convert to energy, joules or kilojoules. And if we had a delta H, delta H tells me kilojoules per mole. So we can use all these things to do conversions for moles. So they're very versatile, and that's kind of our go-between. That's how we navigate chemistry. So before we get into solutions then, we need some ways to deal with our solutions. We need to figure out solubility because many reactions take place in solution. So our solubility rules, we said all nitrates dissolve. Anything attached to a nitrate is soluble. All alkali metals, that's column 1, will dissolve. So anything with sodium in it, potassium, lithium, rubidium, cesium, those things will always be soluble. We say all halogens will dissolve. Anything with chlorine, bromine, iodine, fluorine. But that one has our exceptions. So except if you have a halogen and it is with silver, lead, those are really the two common ones that we need to know. Silver and lead, those are not soluble. Silver chloride will not dissolve. Lead chloride not dissolve. So those are often our precipitates. And then we'll never use it because it's not really a functional chemical in everyday life, but mercury is also an exception. So mercury chlorides will not be soluble. When we get into solutions, we need to know those solubility rules to see what's going to be aqueous and which one is not. This is going to dictate all of our chemistry. So solutions. The first thing we need to come to is dissociation. This is, I can't spell. Dissociation. This is something that trips people up all the time because there's a difference when we say, oh, I have 1 molar calcium chloride. That's aqueous. Aqueous means soluble. It dissolves and it dissociates. That 1 molar calcium chloride doesn't really exist. Those ions separate. So when you're doing your math, you don't really have 1 molar calcium chloride. You have calcium ions that are aqueous, and you have chlorine ions. Now the chlorine ions dissociate twice because there are 2 chlorines. So we get 2 separate chlorines that break off. That means the concentration of those chlorines is twice the concentration of the calcium, because my 1 molecule has 2 chlorines in it. So when they break off, I have twice the concentration. That makes life a little bit harder when you are trying to keep track of the ions, because they're never going to give you the ion concentrations, they give you the molecule concentrations. So you need to remember that there's 2 chlorines there. So if we had an example with 1 molar silver nitrate and 1 molar calcium chloride. And we had a liter of each. Okay. First thing we need to do is get a balanced equation. So what's going to happen here? We've got the silver nitrate is going to react with the calcium chloride. This will be a double replacement, and we're going to make calcium nitrate and and silver chloride. So 2 silver chlorides, 2 silver nitrates, my equation is balanced. But that is my total overall reaction. That is not the net ionic equation. So let's get the phases back in here. Aqueous, aqueous, and on the other side, this is where our solubilities come into play. All nitrates dissolve, so this is aqueous, and chlorides that have silver are not. So this is a solid. That helps us identify our net ionic equation, which is what we're really interested in. We need a net ionic equation. The only thing that reacts is the silver and the chlorine, aqueous, react to make silver chloride, solid. The calcium and the nitrate are spectators. The nitrate is aqueous here, and it's aqueous here. The calcium is aqueous here, and the calcium is aqueous here. They didn't do anything. They are spectators. So my net ionic equation is going to be another limiting reactant problem, but you have to do it with individual ions with our mole charts. Okay, so you got to keep track of the volumes and the molarities here. So 1 liter of 1 molar silver nitrate gives me 1 mole of silver. But 1 liter of 1 molar calcium chloride, there are 2 chlorines there. That's going to give me 2 moles of chlorine. And since they're in a 1-to-1 ratio, we can really easily see here that the silver is going to be my limiting reactant. And the chlorine is going to be excess. So the silver is going to be, there's nothing left. The chlorine is going to have 1 mole left. My silver chloride, I have 0 of that. I'm going to gain 1 mole of that. And since this is a solid, we're going to need to convert it to grams to see how much is left over. My silver concentration is 0. My chlorine concentration is, now it's aqueous, so I need moles per liter. I need the total volume. So let's look at all the different calculations that we can do with that. What do we need to be able to handle with a problem like that? Well, the spectators. The spectators do not react, but their volume does change. So anytime you have a volume change, you do need new molarities. The calcium is a spectator, the nitrate is a spectator. 2 ways you can think about these when you have volume changes. If you know how many moles they have initially, that's an I, you just divide it by the total volume because you had a volume change, so you'll get a molarity. Or, if you know their initial molarity and volume, M1, V1, you know their final molarity if you know their final volume. So you can convert to their final volume. But this is the molarity. This is where people always get tricked. These are ions. You're not dealing with the calcium chloride and the silver nitrate. You're dealing with just the calcium and just the nitrate. So sometimes you might have more than what the molecule shows you if it dissociates more than once. We also want to be able to handle these things with pictures as well as math. We want to be able to draw what substance is the precipitate. We want to show that the limiting reactants do not exist in the picture. They are totally consumed. The excess reactant is present, and if we had the molarities, we could draw the relative molarities. The spectators are present, and relative to one another, do you have more of one versus the other? Are they equal? That's a very important thing. You want to be able to show that they're in the correct ratio. Okay, and the molarities are going to show you that. So you want to consider the molarities of all of these things. So solution chemistry can be pretty complicated. It's limiting and excess reactant problems, simple stoichiometry, but you're doing it with ions and solubility rules instead of strictly grams and normal stoichiometry. And you have spectators that don't react, so you just got to keep track of everything. Another reaction that we're gonna deal with here, if I kind of move this up to the bottom, we want to be familiar with combustion reactions as well. Combustion reactions are very formulaic. You have some sort of hydrocarbon that you're burning. You always need oxygen for a combustion reaction, and this is generic. There's variations of this, but you're getting CO2 and water. And we analyzed combustion reactions with percent compositions and combustion analysis and empirical formulas to figure out hydrocarbons. So we want to be familiar with that construct as well. So I'll just throw combustion down here at the bottom. And there is our first half of the Big Idea 3 overview. The next thing we're going to touch on with reactions is the energy of reactions. Now we're going to spend a lot of time later on thermodynamics, but often when balanced equations are written, we see their enthalpy term, which is our delta H, and it is in kilojoules per mole. And we can do stoichiometry with that. It doesn't have to be 1 mole. If your coefficient of the molecule you're talking about has a 2 or a 3, that energy could be applied to those molecules based on the ratio of their coefficients in the balanced equation as well. But there's lots of different ways enthalpies can be related. So just pay attention to the units and how it's presented. But in general, right now, we're just looking at is something endothermic or exothermic? So in our exothermic world, we have energy being given off. Our reactants have more energy than our products, so our delta H term is negative. And the negative energy is just directional, energy coming out of the system into the surroundings. We will talk also about, when we get into kinetics, in these graphs, we talk about activation energies. So we want to do that. And then it's not totally outside of the realm. We also talk about reverse activation energies. Another type of graph that we have is going to be an endothermic one, where the reactants have less energy than the products. That delta H gap right there is going to be positive. The activation energy is still going to be higher. And we can still have a reverse activation energy. So this is just energy going in or energy coming out. And that's all that we're going to touch on for energy right now. It goes with reactions. We can do stoichiometry with it, but we'll do that later when we get to thermodynamics. The next section we're going to do in reactions is going to be redox. And assigning oxidation numbers is the start of it. We have some really simple rules that we need to follow. It all has to do with electronegativities, but we kind of make generic rules too. Hydrogen only has 1 electron. It's always going to be +1. Anything in its natural state, any element, is going to be neutral. So H2, for example, would be 0. Where hydrogen ions would always be +1, or if hydrogen is bonded to something, it's +1. Oxygen is generally one of the more electronegative elements. It is always going to be -2, but it has some notable exceptions. Hydrogen peroxide is one you should always be aware of. H2O2, since hydrogen is not able to complement the oxygen with a +2 stage, the hydrogens are always +1. Those oxygens are going to defer to the -1 stage, and that's a really, really common peroxide. All peroxides, it's a polyatomic ion that has 2 oxygens in the -1 state. Anything ionic has its normal charge. So this is where we say things that are ionic have charges, but covalent structures, they don't have their electrons evenly distributed anyway. They have oxidation states. So we don't say that covalent things have charges because it's not a full charge, but we measure these redox oxidation states in covalent molecules and polyatomic ions as well. And like we said, anything else that you can't classify, those will just get you started, is based off of electronegativity values. So the higher the electronegativity value, the more likely it is to retain its normal oxidation state, its normal charge. So in a molecule like ICl3, chlorine is more electronegative. Chlorine is going to retain its -1 charge, oxidation state, and iodine in this case would then have to be +3 to compensate. So the more electronegative one stays normal. Those are just a couple of things to get you started. The other thing we did with redox reactions are half reactions. So we need to be able to balance half reactions as well as figure out how many electrons there are, etc., etc. So a half reaction would be like we've got 6 electrons plus 14 hydrogens plus Cr2O7 2 minus. 2 chromiums, 3 pluses, and 7 H2O. So we get this half reaction here. We balance the atoms, we balance the hydrogens, the waters, and the electrons. We want to be able to add half reactions together. We need to be able to balance these. This one is in an acid because it has the hydrogen molecules, and we always start with those because it's going to be easier to do that. We need to be able to balance these in a base. And how we would do that for this one, we'd have to add, this one has 14 hydrogens, so we'd have to have 14 hydroxides on both sides. We'd have to combine like terms and cancel out species to get the number of electrons the same on both half reactions if we had 2 half reactions that we were trying to add together. So given a half reaction, you want to be able to balance it and then take 2 half reactions and add them together based on the number of electrons they have. Another way that AP will approach these problems is by giving you a full balanced reaction that already has both half reactions together and balanced and everything's happy. And they're going to ask you to deconstruct it and find out what's oxidized and what's reduced. I'm going to run out of room. 2 plus, all right, let's get this on there. Plus 4 H2Os. Okay, so they give you this reaction. The electrons aren't there because they're already canceled out, so you get to figure out how many electrons are there being balanced in this reaction. If you put all the oxidation states on everything, you could find it really easy, but what jumps out at you, you're trying to look for things that go together, are going to be these irons. And then the most likely other culprit, it's not going to be the hydrogens or the oxygens, unless you see something in its natural state, you know that it's 0 on one side and it's not 0 on the other, is going to be this manganese. The iron's really nice though, because it says we have a +2 state here and a +3 state there. There's 1 electron being transferred. And since they already have this balanced for you, it has a coefficient of 5. So that's actually telling us that there are 5 electrons being transferred there. That's the easiest way to find the electrons. The iron is being oxidized from iron 2 to iron 3. And if we looked at the permanganate, we could see that its oxidation state is positive 7 over here and positive 2 over here, because that's already given to us. So it's going, there's one of them, the coefficients are 1, going from 7 to 2. So that's 5 electrons as well. Either way you wanted to do that, you could find 5 electrons. And we don't total those up. There are not 10 electrons being transferred. There are 5 electrons being transferred from the iron, which is being oxidized and losing electrons, to the manganese, which then accepts them. So we need to be able to deconstruct half reactions as well. The last that we're going to look at is going to be galvanic cells in electrochemistry. So when we look at a galvanic cell, we need to be able to, again, use half reactions, reduction potentials, their voltages, to see how batteries operates. So if we were given a half reaction that was, or a reduction potential of 2, copper 2 plus 2 electrons makes copper, and then zinc 2 plus 2 electrons to make solid zinc. The positive ones are going to be aqueous. The neutral elemental ones will be solids. You're always given reduction potentials. The copper one is 0.34. Oop. And the zinc potential is negative 0.76 volts. So we have to make a decision. These are both being reduced. We can't put them together if they're both accepting electrons, because one of them needs to be oxidized. They have to come in sets. And we need a positive voltage. So real quick, we can see that we need to reverse the zinc reaction, because to get a positive voltage, this negative 0.76 needs to be positive. So if we reverse it, we can do that. So let's make this zinc turns into zinc 2 plus 2 electrons, and the cell potential is now positive 0.76 volts. We don't need to then worry about this. We'll add these together, and we'll get a final balanced reaction of copper 2 plus solid zinc makes zinc 2. Or zinc is always plus 2, just zinc, aqueous zinc, plus solid copper. And the cell potential, if we add those up, is 1.10 volts. This is a really good point to mention, that if we were to use coefficients in here, you remember that coefficients do not change cell potentials. They remain totally what they are. We can make them positive or negative if they go forward or backwards, but they will not change. We're not going to multiply them by coefficients if we had them. Along with that, we want to be able to draw the battery for this cell. So if we had our solutions, we would have, let's make the zinc over here, and the zinc ions are in solution. Solid copper, and then aqueous copper 2. We need to connect them with some sort of salt bridge, and a wire with a voltmeter, usually just to read the volts. Now over here we saw that the copper is going to be reduced, so that's going to be my cathode, and the zinc is being oxidized. That's going to be my anode. So the half reaction taking place at each cell, we have zinc turning into zinc 2 plus 2 electrons. That shows us that this electrode is actually dissolving. The mass of that one is decreasing because it's going from solid to aqueous. On the copper side, the cathode, we have copper 2 turning into solid copper. Sorry. And it's going to take 2 electrons to do that. So on this one, the electrode mass is actually gaining because the aqueous is depositing on top of it. It's getting plated on top. And when all of this works, we can see the electrons are going from the anode, they're coming off of the zinc, and they're going across over here to the copper, onto the cathode. What happens is we get a negative built-up of charges. On this side, there are a lot of negative ions. All the electrons are moving over here, which means they are being depleted over here. So there's a positive buildup on this wire. To compensate that, the salt bridge takes all the negative ions. If we had NaCl, for instance, all the chlorines would come down here. These negatives are going to deposit to counteract the electrons. And then the sodium ions are going to come this way to counteract all of those negative buildup of electrons, just to keep the solutions neutral. They have to be neutral. We want to be able to write this in cell notation or line notation as well. So we would have zinc on the anode, a phase boundary turning into zinc 2 plus. We always go reactants to products. So zinc solid is turning into zinc aqueous. Then I have a salt bridge, and then the copper 2 plus is turning into copper solid. So there's a phase boundary between all of those things. And then don't forget, sometimes you need to add platinum if you have no solid. Because you still have to have a metal in there to conduct electricity and complete the circuit. But if there's no solid, if your reaction is taking place in solution, you need an inert metal, so platinum will take care of that for you. The last little bit here, I'll put room here in the bottom, is when we do electrochemistry, this last little bit is electrolysis. We need to be able to do the conversions that we use with amps and volts to plate out or deposit grams, a certain number of grams of our metals. So when we have negative solutions, negative voltages, they are not spontaneous. We can make them spontaneous by adding a current, putting electricity in. And the couple conversions that we need for that is Faraday's constant, which is approximately, for any, it's 96,500. You have it on your equation sheet. But for multiple choice rounding, it's 100,000 coulombs per mole of electrons. And then we need to remember that an amp, so if you had a 5 amps of your current going in, that would be like 5 coulombs per second. So that gives us a way to convert electricity and time, and then we could go into grams and molar masses. You will also need half reactions. How many electrons are being transferred in the equations, because Faraday's constant is 100,000 coulombs per mole of electron. So if my zinc reaction had 2 electrons, well, 2 electrons is going to give me 1 mole of zinc. So we have some stoichiometry conversions with the electrons and the half reactions as well. And that just gives us a way to convert into grams, so we can see how much metal will actually deposit over a certain amount of time. And that wraps up all of our